This is just a quick reminder that you should feel free to pause the video if you ever feel you want more time to think and write. Welcome to section 5.6, day 2, applications and models of compound interest. So here is another kind of curve you might not have ever seen before. The table's a little in the way, but you can see in your notes it's got this curve. This is found in biology a lot. Anytime you've got a population and it's going to grow, you know that populations grow exponentially. But sometimes there's this limiting factor. Like any environment is going to say, look, there can only be so many fish in this pond. There can only be so many locusts in this field. There can only be so many bears on this eating. There's only so many bears on this chunk of ice, and there are going to be only so many humans on this planet. Anyway, there is this limiting growth right here. So what would happen is, as you approach the top of the curve, it doesn't keep on growing exponentially anymore. It starts to level off. That's what's called limited logistic growth. Here's a really great curve. You can see, wow, the population is exploding, and as overcrowding takes place and just the natural carrying capacity of whatever environment they're in, then the population starts to level off once it reaches the carrying capacity. You can see that in growth in a lake, for example. A lake is stocked with 400 fish of a new variety. The size of the lake, availability of the food, and the number of the fish restrict the growth of that type of fish in the lake's limiting value of 2,500. There it is. We're going to say that this line right here is 2,500. You can get pretty close to it, but you never pass it because that's just how many the lake can hold. The population gets closer and closer to this limiting value, but never reaches it. The population of fish in the lake after a time t in months is given by the logistic function, 2,500 on the top, and then 1 plus this crazy thing over here. You can see that E is going to play a huge role. So we can take them at their word that this function works, and we can graph it. You type it in a Desmos, and this is what it looks like. Find the population after 0, 1, 5, 10, 15, 20 months. Plug it in. I used a table, and this is what you get. You can see it's approaching, but never quite reaching 2,500. Next example, carbon dating. Example 5, carbon dating. The radioactive element carbon-14 has a half-life of 5750 years. The percentage of carbon-14 presents in the remains of organic matter can be used to determine the age of that organic matter. Archaeologists discovered that linen wrapping from one of the Dead Sea Scrolls had lost 22.3% of its carbon, carbon-14 at the time it was found. How old was the linen wrapping? So we don't know what the K value is. We actually don't know what the K, P, P0, or T values are at the very beginning. We know that it has a half-life of 5750 and that the one particular wrapping has lost 22.3%. That means 77.7% remains. Anyway, in order to find the K value, we can use the formula from yesterday, the half-life formula. K is equal to natural log of 2 over 5750. We do that and we get a K value of 0.00012. We can plug that into here. Notice this equation it has the negative symbol here. P is equal to P0e to the negative kt. If you have a negative, that means it's decaying. It's getting smaller and smaller. Now, dividing both sides by P0, we get P over P0. And we don't exactly know what P is. We don't know what P0 is, but we know that the fraction is going to be equal to 77.7%. This fraction gets replaced here, 0.777. That's the decimal version of this percent. And then the K value that we calculated goes here. And now all of a sudden we have an equation that we can solve. You can rewrite this as a logarithmic notation. So you might ask, what is the exponent? It's right here, negative 0.00012t. The base is e, and the power is 0.77. Another way to think about this, going from here to here, is that you could also take the log of both sides. The log of this side is this. The log of this side cancel out the e's, and you're just left with the exponent. In any case, you can divide both sides by negative 0.00012 and calculate it, and t is equal to 2103, which is actually historically accurate. There's lots of other evidence that says the Dead Sea Scrolls were written just before the time of 0 AD. If you check, you're not going to find any curium in the Dead Sea Scrolls. That was named after Pierre and Marie Curie, French physicists and chemists. That's number 96 on the periodic table, curium. This is exponential growth. This is what we talked about, and what we just saw in the Dead Sea Scrolls example was exponential decay, and this is new. The only difference between these two is a negative symbol. Negative KT, positive KT. But what that's going to do is it's going to reflect the graph. Although here it's going to be exponentially growing, here it's going to be exponentially decaying, going down. That's what that little negative will do. The formulas are still the same. K and T, K times T is equal to natural log of 2, K times T is equal to natural log of 2. Here's exponential and logarithmic curve fitting. So you remember this little symbol, the tilde, that helped us form a curve to data. Well, you can do the same thing here. These are the parent functions, abx, ab negative x, a plus b log of x, and logistic, a over 1 plus b e to the negative k, x. Those are the parent functions. So if you wanted to say that consumer spending in billions on video rentals was going to be exponential, then you could make a case for that. It's going up like this. You can plot the points and type into Desmos y1 is equal to a times b to the x1. If x1 and y1 are the top of your tables, it'll figure out what a and b are. I'd like you to do that right now. I'd like you to figure out what this is. You can see the r-squared values are pretty close. It's very close to 1. If they were all perfectly on an exponential graph, it would be r-squared is equal to 1. But here we got a is 2.16145 and b is equal to, I want you to figure it out. This is what it'll look like. And once you figure it out, then I want you to begin assignment 5, F2, copy the problem list, do the first problem. I'll see you in class.